Ladies and gentlemen, in this tutorial session, we will show you how to make a model of a precast girder beam in the new preprocessor, the new version of ATENA 2025. So the structure that we will analyze, you see on the screen. So they are precast reinforced concrete pre-stressed girder beams with the length of 12 meters. That means 39 feet or 472 inches. The web thickness is 6 inches, 150 millimeters, and the height of the beam is 1300 millimeters, 51 inches. So we go now to the software ATENA. So here you see the typical input screen of ATENA software. And we have imported the individual important sections of the beam and also a side view plan of the beams which we will use now to create the model. So the purpose of this tutorial is show you how to quite effectively and quickly create and generate a model of such a beam. So the first steps were to import these sections and arrange them at the right locations. And now we will start defining the model. As you can see here, we also have the location of the stirrups. So we have imported the stirrups at the locations where they are changing. So let's start first with the definition of the beam. So we will create the beams which we already have prepared our layers where the beam volumes or beam entities will be created. So first we want to create the ends of the beams which have a little bit thicker web. And we will do that by creating volumes between these sections. And for that, we use this create solids from two opposite surfaces tool button. So I click on that and now I start selecting first surface, the other surface. I complete it by hitting enter. So now we have the one part of the beam. Now we do the same thing on the other side. So now we have the end parts. Now I want to create these transition regions. So I use this layer beam transition and I will create these two surfaces. You see now the surfaces have a little bit different geometry. Now it is maybe better to switch to wireframe model. So I now again select one surface, opposite surface, click, hit enter. You see the transition region is created. Now I do the same thing on the other side, enter, and I have the transition regions. Now I go to create the middle region. So I again activate the layer where I want this middle part to be present. It is always a good idea to divide my structure to various layers. That means I need to prepare these layers and then create the structure on these individual layers. So now you see we have completed the beam generation. So we have our beam. I can switch to a different visualization. I will use the outline transparent model, which provides a nicer view of the model. Okay, so I see I have a beam which consists now basically from 5 parts, the ends with the thicker web, then the middle part which has the thinner web of 6 inches, and then I have these transition regions. I will save it under some name so that I don't lose my data. Now the next thing will be to create these loading plates. You see they are defined on this on my view, side view of our girder. So for that I will create them on this loading plates layer, and I will first copy these side view lines to be present or to be on the edges of my girder. So for that, I will use this translate geometry option. Now I don't want to collapse. I want to create a copy. I don't want to respect the layer because I want them to be on the active layer. And now I'll be copying the edges, so the curves should be only selected. Now I go and draw. You see I have this line which I don't want in the copy, so I deselect that, and now I click the starting point, ending point of my copy operation. Now you see there's the one, the lines already exist at the location where I want them. I now do the same thing with this bottom, one of the bottom plates, same thing on the other side, starting point, end point, and now I have my the beginning of my edges. Now I don't need this side view, so I will deactivate it from my screen. And now I will extrude these plates to be along the whole depth of the beam. So for that I will again use this translate option. This time I don't want to copy, I want to do extrude, and I want to respect the layers. So I want them to be on the layer of these original sides. Actually, before do that, I need to change them because now I would like to copy them as surfaces, but they are not yet surfaces, they are lines. So first I need to go and create a surface, side surface of each plate. So I use this create surfaces button. I click on any of these edges. The program recognizes that this is the only possible loop. So I hit enter. And in this way, I quickly create these side surfaces of my loading plates. And now I will go and extrude these surfaces using this extrude command, surfaces. So I click surface. Now I click define the extrude vector. When it is completed, one is already ready. So now I create the other loading plate on the other side and also the top one. Actually, those were at the bottom. I have supporting plates, and this one is a plate to apply the loads. So you see now we have basically the beam ready along with the loading plates. So what is now the next step? Next step will be to generate the reinforcement. I told you for that maybe I'll deactivate now the beam. And you see I have my reinforcement here. So first I will deactivate the reinforcement I don't want to copy. So first, because I know that these reinforcement basically extend along the whole length, so I will use them now to copy them along the whole length of the beam. Again, I will use this copy translate operation. This time I don't want to do extrude, I'll be using copies. And I want to respect the layers. So I'll be using these reinforcement layers. And I will be copying curves. So I go now and I select the curves I want to copy to simulate the reinforcement. With the control, I can pick another, holding the control button, I can copy, or I can select all the reinforcement I want to copy. And now I define the vector. So I start, original of the vector is 0, and the second point I use this set 0 button to put all my coordinates to 0, and now I need to know that the spacing of the reinforcement at these end parts of the beam are 3 inches. So I'll be copying by 3 inches, and I can see how many I need. So 7 is not enough. So I see I need to have at least 12 bars or 12 stirrups in this end point. So I do apply. I have them generated. Now I will select them again. With control, I can select all the parts, all the stirrups I want to copy. This time, again, starting coordinates of the vector are 0. The end coordinates of vector I first 0, 0, and then I know that the spacing should be 4.5, and I will need much more copies, maybe something around 86. So I need 88 to copy all these stirrups along the whole middle part of the beam. I do apply, and now I have my beam, my reinforcement, my stirrups, or top stirrups and bottom stirrups for the middle part generated. So I go to finish it on this right end of the beam. So again, I go to this copy command. I'll be copying, probably not 88 times, but only 12 times. I need to select the curves, or basically the reinforcement, stirrup definitions. And again, I define the vector, which in this case has the coordinates 3, 0, 0. And with this, I can check if there are enough of these copies, maybe one more, to be at the end of the beam. Okay, when I like my arrangement, I confirm it by apply button. And we have now all the top and bottom stirrups of the bottom flange and the top flange ready. Now I need to go and copy also the stirrups for the web, and they are defined here. So now I go again, and actually what I will see that if I select this reinforcement, you see that the reinforcement is still divided into individual sections. So I will connect it to connect them together to create a single loop, single stirrup out of them. And for that, I use this option under the curves table. There is an option compose, which we can use to define a stirrup consisting of a whole closed loop. So I confirm it by hitting enter. And now I can use and copy, I can use this closed stirrup and copy along the parts of the beam where it should be. So I go again to the translate command, and I select this blue stirrup. Starting point is again 0, ending point should be 3, 0, 0. And I can rotate a little bit and see if they are in the right position. Actually, this one is already wrong, so I remove one more copy. So I need only 12 copies, so I do apply. Now I have the stirrups at the left end, so I need to put them also in the right end. So I will take this rightmost stirrup and precast starting point and end point should be. I have to look here, should be somewhere here. Okay, and now I will again copy this stirrup to the in the right part of the beam, where I know the spacing is 3 inches, and I need 12 copies of it. So I do confirm with apply. So now I have almost all the stirrups. I just need to copy also this middle, this stirrup for the web, which I have on this layer. So that's this green entity. So again, I use this copy command, and I pick this stirrup. Starting point is 0, ending point I know should be such that I have spacing 4.5 inches. And now I just need to define a number of copies. I know from the last time it was 87. Let me just check here if it is correct. Yeah, if I zoom in, yes, I see all the stirrups will be at the right position. So I do apply. So now you see I have all the reinforcement ready for my beam. So I can check a little bit whether it is correct. So if I select also the concrete part, so you see I have now the geometry, basic geometry of my structure is ready. And now I can go to define the material properties. So by material properties, I go to this item in this input data tree on the left called materials, and there you see you have the individual items for the most typical materials. So this beam is made of concrete, so I will create a concrete material. We know that for this beam we know the cubic strength, which is let's use imperial units. We know it is 12 ksi, so we can generate material properties from the cubic strength. You see in ATENA you can easily switch between the units here, so we can check what was generated. So we see that the tensile strength 0.6 was generated, compressive strength 10.2 ksi. So we can also give it a name, 12 concrete 12 ksi. Okay. Now we will need also some material for these loading plates. So for that we will use elastic material. It will be steel, and we can give it a name, steel plates. Okay, so we have now the materials we need, and we will need also reinforcement. We have reinforcement for the stirrups, so we can create reinforcement with this strength of 72 ksi, and we give it a name, stirrups. Here we can also check what is the stress strain relationship. So we will first have elastic up to 72 ksi, yield strength, then there is hardening up to 5%, and then there is a rupture of the reinforcement. So here of course you can modify your material law or stress strain diagram for the reinforcement as you need. So we can create this material, and I forgot now that we need one more material for the strands, because this beam is pre-stressed, and I forgot to generate my pre-stressing reinforcement. So let me turn off the stirrups so that I can see them better. And you see in my importing of the original section, I have imported here the location of the strands, of the pre-stressing strands. So now I need to go and copy these strands or create these strands. So I will deactivate my beam so that I can pick the strands more easily. Maybe I'll take off this cut also. And I will use that side view so that I can use it to copy the strands along the whole length of the beam. So now I will go and create these strands. So I make my strand layer active, and I will again use this translate option. I will extrude, and I'll be extruding points to create lines. So now I select my strands definition points, and I will extend them along the whole length of the beam. So now I have the strands generated, and we can see how they are, and I need to now define the material for them and to assign them to these pre-stressing strands. So I go to reinforcement, create the material for them. It will be a tendon material. Well, it has this yield strength of 1860 megapascal, which, as you see here, corresponds to, well, let's round it to 270 ksi. So we generate that. We will call this material strands. And okay, here we see the law. So again, it is a bilinear law with rupturing at about 5% of strain. So now we have the materials, but we need to create these reinforcing types. So let's go with the tendons. We create a tendon. We give it a name, strands. We know that the area is 15.7 millimeters. And we can define a bond. Either can be perfect bond, unbonded tendon, or bonded. So we say it will be a bonded tendon. It will be fixed on both ends because there are some pre-stressing anchors. And we can generate a bond law. Here you see the available bond laws in the software. So we'll use the FIB model code 2010. And we know that our concrete strength is 12 ksi. It is smooth reinforcement, color drawn wire with good quality. So we say okay. Now we can go and check the bond function that was generated. So you see the shape of the bond. Again, here's a table. You can modify if you need and have some more data about your bond properties. And now we assign it to these strands. Now the same thing we will do also for the stirrups. So I display them, activate the appropriate layers so that I can assign them easily. Now I go to reinforcing type bar. I give it a name. Stirrup. It will be a bar. It will use this material stirrups. The diameter is 10 millimeters, or if you say, yeah, it's 0.39 inches. And We can also check the bond, generate the bond model, again use the FIB model code. Again, we have our concrete with 12 KSI. It's a ripter reinforcement, unconfined, good bond quality, and we can generate the bond law. If you look at it, now this is the bond law that we'll be using. And the bond strength is about 9.4 megapascal, which corresponds to about 1.4 KSI. And now we can assign it to all these stirrups. They are all of the same type. So now we should have everything, all the materials should be defined. So we can go and check whether our definition is correct. We have the possibilities here to check or to color our structure according to the various entities. So we can, for instance, color according to the materials. So here you see we have the strands with gray color, blue color are stirrups. And we can also now check the beam material properties. So, or we can check also the Carnegie geometry according to the assigned types. So if we go to, okay, so we see, yeah, now we see that I couldn't display the materials for concrete, because that's because we have not assigned them. Yes, that's why we couldn't see. If we look here at the displaying the materials, you see there is no material assigned to the beam. So we know that we have made a mistake, and we still need to assign the materials to the beam. And that's because we first create a material, and then we have to define a building element type. So we create a type of beam for this for the beam part. So we click on beam types, create a static model. We will use solid, concrete 12 KSI, and we now assign it to these individual parts of our beam. You see, now we see that it is really of concrete. And now I go to create the plates. So here are the plates, and I again click on this plate in this bottom table where I see I don't have any plate types. So I create a new plate type, and it will be using material steel plates, that the one I have defined previously. And now I will assign it to these entities. Now I can go back and check that indeed I have the materials assigned as we want. If I turn on the reinforcement, you see now that I have all the materials, strands, stirrups, steel plates, and concrete. All the materials are there. So let me turn off the reinforcement so that our view is a little bit not so complicated, not so many lines. So now you see we have our model the geometry of the beam assigned with concrete properties, steel plates, elastic material for the steel plates. Also, we have assigned the material to the reinforcement and to the pre-stressing strands. So what is the next step? We go to define the loading. The loading is organized to load cases. If you go to load cases, you see there are some predefined default most typical load cases like body force, supports, and forces. But in this case, we will need one more load case for the pre-stressing. So I create one more load case for pre-stressing. So now we have altogether 4 load cases. And we can start defining or assigning individual loads to these load cases. So first, we need to define the boundary condition and loads, such as supports. But there is one more important thing. We notice that we define these loading plates totally independently to the beam. So we now have to tell the software that these loading plates should be connected to the beam. And for that, we will use a fixed contact, which we put into load case supports. And this is the fixed contact condition, which can be used to fix 2 parts of our model together. So we first assign the master surfaces. For that, I will use the wireframe model where I can pick the surfaces more easily. So I select always the bottom surface of each plate. I mean bottom surface of the top plate, and it will be the top surface of these bottom plates. So one on the right side and one on the left side. With enter, I confirm, and it automatically asks me to define the master condition. So you see here, it's now I'm defining the master of the same name. It always use this name, which is generated here by default, to identify which connections should be tied together. So now I will assign this master condition to the bottom, to this bottom surface of the beam, also this one, and the top part of the beam for the top loading plate. So now I have this master slave condition, which is called fixed contact. And now I can go to the other conditions. So I will need to define the supports. So I need a line support here and line support here. I want to model a simply supported structure. So my support on the left will be fixed in Z direction and X direction. So I'll assign it to this one, to this line. And then one more line condition to this right loading plate. This one will be fixed only in Z direction. Now we need to prevent any rigid body molds. We need also to fix the plate or the beam in Y direction. So for that, I will define 3 supports at points, which will be fixed in Y direction. And I'll put it to this point, and this point. So you see now that my beam is also fixed in Y direction. Maybe I'll outline it a little bit so that you can see it more clearly. So we have connected the plates, loading plates with the beam. We defined the supports as simply supported structure, also fixed the beam in the Y direction. And now we need to apply the other loads which remain. first one is the body load, which will apply to the volumes. So that's why I click the volume here. And it will be the body force load case. Weight in Z direction should be minus 0.09 inches, pounds per cubic inch. And now assign it to the volumes of the beam. You know, the beam consists of 5 volumes, 2 ends, 2 transitions, transition regions, and 1 middle region. So now I have the body force. Then I need to apply the force, which I will load from the top. So I select the forces load case. It will be a global load in Z direction, and we know that the weight should be, I will apply it as a line load. The total weight is should be expected around 600 kip divided by the thickness of the top flange, which is 30. So I end up with minus 20 kip per inch. And I will apply it along this line, top line of my loading plate. So I have the loads, I have the body forces, I have the supports, and what remains is the pre-stressing. So I need to apply my pre-stressing load. So this will be applied to reinforcement, which is indicated by this button. Pre-stressing, and it will be, I define it as initial strain, 0.7%, which creates the pre-stressing stress of about 1,400 megapascal. So at this point, all the loads and supports are defined, so I can go to the next step to define my task. But before going to define my task, it is always a good idea to define some monitors. Something to monitor the applied load so that we can display kind of a load displacement diagram as we will be loading our structure. And good load displacement diagram is to monitor the force and to monitor the deflection. So I'll create one monitoring point which will be monitoring the load. I call it load F. It will be the external force in the Z direction, and I will apply it as a summation of the line of the forces applied along this line. So this is one monitor, and then I need one more monitor where I'll monitor the deflection. So I'll put a monitor monitoring the maximum deflection of this bottom surface. So I'll use a surface monitor. This time I give it a name deflection, and it will be monitoring the displacement in Z direction. It should be the minimum because it will be negative in Z direction, and I apply it along this bottom face. All right. So I think at this point we are almost ready to start our analysis. However, we should realize that we have not yet defined any meshing properties, because our beam is a structure which can be nicely, even though it has different cross sections, it is still kind of a longitudinal element which should be easily modified using extrude option. So we define, we will select that we want to use the extrude option for the beam, and we therefore assign it to the volumes, to the individual volumes of our beam. We want them to be extrude, but to be able to use extrude, we need to make sure that all these regions are compatible so that the extrusion will be the same along the whole length of the beam. and therefore we need to go check and verify that, so whether these volumes are compatible with each other. And this is done through this make extrudable command in the solids table. So I select this make extrudable. It asks me to select the volumes that I want to make extrudable, and I select again all of them. And you see at the bottom here, it is always a good idea to observe the messages. It said that two solids, 3 and 4, were fixed, and the other three, 1 to 5, were already compatible with each other, but the others were fixed. So now we can go and we can check our mesh. So we go to this mesh generator. Here we have to check the default sizes. Now they are too small because we are working in imperial units. So we switch to, we define the uniform mesh size to 20 inches, and we can preview the mesh. So let me switch to the outlined model so we can better see our mesh. So you see our mesh is almost correct, but there are two things we don't like. I would like to have quadratic elements along the, or basically brick elements, not these wedge elements. So no triangles here on the sides of our model. In addition, so this is one thing that we need to modify. And in order to do that, we need to specify on the surfaces that we want to have a mesh type, which will be quad dominant. So let me go now and define to these surfaces of our okay, I need to activate the right layer because this layer with the cut B is not there. So I cannot pick the surface. So this is the surface. This is the surface. This is the surface. These are the six surfaces that I need to define as quadratic. So we can click we can check here. If I click on this definition, I can check that indeed all the surfaces now are defined with the quadratic mesh. So I can go to my mesh generation and verify whether it is better now. Indeed, now you see that in the cross section we have quadrilaterals through the cross section of our beam. And you see also the beam, the structured mesh, or the software has the tendency to make the mesh finer along the points where there are some load application. But I would prefer to have a uniform mesh. So I go to the mesh size. So for these lines, I want them to have the same mesh with the same numbers and with the equidistant spacing. And so I can define, for instance, 60 elements along the length of this middle beam part. So let's see if it is better now. Yes, this is the mesh I think we can like for this beam. It's preferably to use for the stress analysis, it is preferable to use brick elements or quadratic elements in 2D. So at this point, I think everything should be ready. We have defined the conditions, monitors, we have the mesh. We need also define now a task. So we go to the task menu and we will create our task, basically define the load history. So this is done by intervals. First we define initial interval where we apply dead load and pre-stress. And in this interval, we need the supports. This we need always. We need the body force. And we will also apply pre-stressing. All this will be applied in this first interval. And we define number of steps. So we will apply it in 5 steps. Maybe there will be some micro cracking, so we don't want to apply it in a single step. So now we'll have another step where we will make the load test. We will simulate this load experiment where we apply the load on the top loading plate. Again, we need to define the load cases which will be active in this interval. So we need supports and we need our forces. The pre-stressing we don't need, the body force we don't need, because whatever was applied in the previous step stays there unless we apply it with a negative sign. So we have the loading clear. Now the solution parameters, now we want to simulate or all the way to peak and post-peak, so we should use the arc length method. And we want to go a little bit above the peak load, which is expected around 600 kip. And of course, we should not go there in only 5 steps. Maybe we should use finer steps, smaller steps. So it is recommended to go to peak in, let's say, 50 steps. So now we have our loading history defined. It consists of 2 intervals. One first interval is where we apply dead load and pre-stressing in 5 steps. And then we perform the load steps by increasing the applied forces all the way up to failure. And we are using the arc length method, which allows us to detect the failure and start scaling the load when we go to post-peak. So with this, we are ready to start our analysis. Let's hope everything is defined correctly. So we can start. Actually, there is one thing I need to check. I'm not sure if I correctly defined the tendon bond properties. Now thinking about it, if you go to bond, okay, fix both. Yes, this was correct, because at the end of the strands, we assume anchors and the strands are fixed there. And with the stirrups, there I should use also fix both, because there are hooks in our stirrups. So now I go and I can start our analysis. Let me pause our model to give you an idea. What happened is that now the program, we create the input file. The preprocessor was closed, but before finishing, it created an input file, which we can see here. This is basically the textual file containing the full definition of the input. And now we are in a software called ATENA Studio, which is used to simulate and control the analysis and allows also a full visual control. So if I resume the analysis, you see how the program is calculating. Now we are in the 3rd step. Here we can display the deformed shape of our structure. You see that we are in the first 5 steps applying the pre-stressing. So the beam is bending upwards, but I will reduce a little bit the deformation scale. And I like usually to display it with solid outline, because later on it will be nicer for the visualization of the cracks. So here I can also show cracks, and I like to show only the most important cracks. And it's also always important and good to define some minimum crack widths. We are working in this model in imperial units. So the minimum crack widths for, let's say, visible cracks, we can specify as 0.01 inches. So now we see how the structure deforms, and you remember we defined those monitoring points that should allow us to visualize what is happening with the structure in more in a more systematic and gives us a better overview of the structural behavior. So we can, with this graph button, we can define these diagrams where on the horizontal axis we will put the deflection, and on the vertical axis we want to put the applied load, and it's better to have it positive, and because we are working in units, force units are pounds, so I will use this 0.001 minus 0.001 multiplier to convert my load displacement diagram into kips. So what do we see here? First, we see that when we applied the pre-stressing, the deformation of the beam went upwards, and then we start applying the load at this loading plate. Maybe I'll rotate it a little bit so it is in the same way like it was in our preprocessor. There we had the x-axis pointing to the right. So we are applying the load here. This load is gradually increased up to failure. We see how the cracking propagates. So we have some bending cracks, also some shear crack developing. And now, of course, we can visualize what is going on. Of course, we have to understand that all this graphic display is somehow slowing the analysis. So maybe it's a good idea to switch to so-called turbo mode by this button on the top right. So with this, the program is running only as such kind of a small bar window. And let's let it run. And maybe we go back a little bit and can explain or can talk about some parts of the preprocessor that we have not covered. So here we always see the mesh as it was previewed. We can turn it off by this button. Let me talk a little bit about the various options here. So at this top we have some basic basic menu items for the file operations. If you go to file, there we can open and save, open most recent, import. Here it's possible to observe the possible imports. So we can import ATENA 2D, 3D files, IGES, GID, and also include import into existing model other ATENA preprocessor files, so-called PRE files. If I go to the next item is the edit, which is most important. For instance, is the copy to clipboard, which we can use to copy the content of our current window and paste it maybe to some document. There is also undo operation. View, it is for loading a default view, defining various models views. Here we can define the contents of these various windows. Geometry, it is the same thing basically which we have in the buttons here for defining and creating or editing individual geometrical entities. Data item is for defining materials, building element types, basically the same things, same operation as we have accessible from this left data input data tree. Finite element mesh is for various commands for input file and execution of custom ATENA commands. Setting contains the various project settings which are general project settings for where about the units that we are using. So here, for instance, you see that's what I mentioned to you, that in this project we are working with imperial pounds, inches, and seconds and Fahrenheit units, but there are other predefined unit combinations that you can use. You may have noticed also that any input you can select other units, but later on and use those units to define your input data. But later on, when the program starts, it always converts to this basic set, and those are the units which are used in the analysis. Plugins is a method how to include various customized Python plugins. For that, I would recommend that you consult the user's manual for ATENA Pre processor. Then this top bar again contains the definition of various important and most common operations. Those are the file input save commands. This is the undo command. This is for zooming and fit to all operations, rotation, moving, light position. This part is for defining points, lines, curves, up to volumes. This is for deleting or selecting. And here we have various copy operations. So let's go now to check how our analysis is progressing. So let's have a look at our model. So you see that we have almost here we can, that's why I recommend to always have these monitors, because now this monitor clearly shows us that we have reached the ultimate load carrying capacity of our beam. We also see it in the deformed shape of our structure, that it is quite well deformed. We see the cracks. Maybe now this deformation scaling is maybe too big. If I go back, if I have some describe a little bit more about this operation, of course you should consult the manual, but very briefly you can add other windows here. So if I click this button, it will open another window, and in this window I can use this activity manager maybe to create a new activity to see maybe only the stirrups. And I can go activate the search here, where are the stirrups. So here I see start the stirrup definition, and it will go all the way almost to the end because there are so many of them. So I create an activity with the stirrups. So I see what are the, here I see the stirrups. I can use this button to show also the outline of the model so that I know how the stirrups are located inside our model. Change the orientation so it is like it was in our preprocessor. And here, for instance, we can look, which might be interesting, to look at the stresses in the reinforcement. So we can see that indeed here, where we have this shear failure, those are the stirrups with the highest stress. And we can check whether they are yielding by, for instance, look at the plastic strains. And indeed here we can see that there is quite a significant yielding going on already in this part. I can open one more window where maybe it will be nice to create another activity for the strands. So I select the strands here. And again put them, show the outline of our model. So this is good because it shows me the location of my strands inside my model. And we can, for instance, display the stresses in the pre-stressing reinforcement. And you clearly see that we are observing a collapse, failure of our. So maybe at this point we can interrupt our analysis. Makes no sense to calculate anymore since we are clearly in the post-peak. And so we have completed basically this analysis. So you can see rather quickly we obtain the behavior of this beam. And I showed you that this runtime analysis or runtime program, ATENA Studio, is actually a runtime post-processor, so we can see how the structure behaves even as it is calculating. But of course, it can serve also as a full functional post-processor. So once the analysis is completed, we can go to post-processor here. And basically the same software, we can now go to explore our results in more detail. If we want to go back to some steps, so we can look along our load displacement diagram and along this history of calculated steps. For instance, we may be interested in the peak load, which we see was here at step 47. So I can go and select step 47, and we can explore now the results at this step. Another maybe, well, the function, there are a lot of functions, there is a large possibility, a lot of functions in this post-processor, a lot of features. I would recommend that you look at the user's manual, or you can also explore the various tutorial problems in our YouTube channel to give you some ideas about the post-processing. The last thing I want to show you is this interesting possibility to visualize the cracks in the interior. So if I go to this view style and I select outline, I can now see how the cracks looks like inside my structure. And maybe it's a good idea now to introduce some filters to really filter out only the most important cracks. So here I see the cracks which are wider than 0.05 inches. Maybe that's too much, too big filter. So in this way, we can obtain quite interesting results of the cracking in the interior of our structure. So with this, I would like to conclude my presentation, and it should have provided you with an overview how to relatively quickly create a model of relatively complicated beam with different cross sections through the length of the beam with quite detailed reinforcement arrangement. So with this, thank you for your attention, and looking forward to seeing you in some future seminar or webinar. Thank you and goodbye.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.